So welcome to this revision of transistors. So the first major transistor that we learn are BJTs. They are of two types, NPN and PNP. So NPN transistors basically have collector supplying the current and that goes through the transistor, and the base is where we give the input signal and we can take the output over here, and the rest of the current drains through the emitter. And similarly, this is a PNP transistor. Now let's understand how a transistor basically works. So you give a source to the collector plate and you drain the emitter plate, and you give some sort of a signal which is filtered through a capacitor to the base plate with certain biasing, and we take the output at this node, and that is how we bias a BJT. And this signal basically tells this BJT how much current to draw from this source. So we get the simple relation, that is IC by IB is beta. So whatever current we send in through this base will be beta times the current that is drawn through this collector. Remember that this is a property of the BJT. We have a similar relation, that is IE by IB is alpha, which is also a property of the BJT, which talks about this emitter current. Now, how does current flow occur in a BJT? So let's take into account the PNP transistor. So I'm applying a voltage here. I'm applying some sort of a voltage here, and I'm taking the output over on this side. So this is just grounded. Now what happens is electrons flow through this direction. So this part of the BJT is actually forward biased. So if I just look at this part, this appears as a forward biased PN junction. So current flow occurs towards this side. Now in the P side, the majority carriers get injected into the N side, becoming minority carriers. Now, due to high resistance at this junction, only a little amount of current comes out of here. So original IC current is mainly retained and goes into this part of the BJT, where once again it switches to being majority carriers and finally gets drained. So if we need to write the exact equation, we can write down IE. So remember that the emitter, base, collector. So E and C are switched for NPN and PNP transistors. So emitter current we can write as basically IC, so the collector current which is coming out of here, and the summation of the base current which is coming out of here. However, if you talk about an NPN transistor, you can see that the collector current going in and the base current also going in, resulting in the emitter current. These are the two equations of current for the BJT. Keep this in mind that even though IC or the collector current it mainly comprises of the majority carriers, it also includes a component ICO due to the minority carriers, since in a BJT these two layers are fused. Keep this in mind that two PN junction diodes attached like this won't act as a BJT, since these two layers need to be fused and this terminal needs to be made high resistance in order for this structure to work as a BJT. So now talking about common base amplifier circuit. So first thing is, this is the VBE, so difference between base and emitter voltage. Note that base will be at a higher voltage, and VCB, or the difference between base and collector voltage. So with that in mind, let's start with the input characteristics. So we check for IE versus VBE, and we see that basically there's a difference between VCB of IE versus VB. So at a higher VCB, the curve is more steeper, and this is known as early effect. And we see that at a particular voltage, the transistor starts conducting, and this is known as VBE on. So it's 0.7 volt for silicon, and remember this value for calculations. Now, if we talk about output, we basically check the current IC, so collector current, with respect to VCB or collector base voltage. This is the part which is important. So this region over here is known as the saturation region. This region is known as the active region or the forward active region or FAR. Now, this region is known as breakdown, where the transistor's internal structure breaks down and IC increases rapidly. Okay, now if we talk about how the diode behaves, in saturation region, both the diodes inside the BJT are forward biased. So basically, VCB and VBE are both forward biased. In the forward active region, the first diode or VCB is reverse biased and VBE is forward biased. In breakdown region, we don't generally talk about what happens. We know that the transistor structure has broken down. In cutoff region, we get both the diodes as reverse biased and we get practical zero collector current. And here, if we see some current, this is due to the reverse saturation current, ICO, and emitter current is zero regardless of whatever collector current we see. So basically, whatever current that comes through the collector will drain through the base, and this part will act as an open circuit. This happens bottom of the curve in the cutoff region. So that is how the linear amplifier works. So the linear amplifier will work in the forward active region where the output is not distorted and the diode's first diode is reverse biased and the second diode is forward biased. Now, in common emitter amplifiers, the first thing is IB versus VBE, like in the previous curve. Note that these two are actually swapped. So the lower voltage is in the sharper curve and the higher voltage is in the less sharp curve. More importantly is the changes we see in the output characteristics. So IC versus VC. Note that IC is plotted in milliamperes while IB is plotted in microamperes. Now, this is basically the base current we are seeing. First change, these curves are now slanted instead of the original straight of the common base. This is mainly due to early effect. Question can come theoretically why this happens. So this is due to modulation of base width in common emitter mode. When we apply a higher VC, what happens is that this depletion regions which are there between the between the two diodes that we consider, these thicken, and as a result this base basically becomes shorter, and as a result what happens is the gradient of charge carriers at this junction increases, thus more charge carriers flow to this side. However, as the base itself is now thinner, there is lesser amount of base current that is able to flow out. So due to these two reasons, that the collector base reverse bias increases, as a result what happens is the distance between depletion region decreases, so the width of the base itself decreases and the charge carriers increase there and IC increases. So since IE isn't constant, IC increases will result in IE also increasing at a fixed IB, and this is what is known as base width modulation or early effect. Keep these 2 points in mind. Now, if we trace this slanted curve, so if this is the slanted curve, if we trace it backwards, we will reach almost 100 to 200 volt in the minus V axis, and this is known as early voltage, represented by VA. The other changes, see, in the common base, we had a well-defined cutoff region below the x-axis. For the common emitter amplifier, The cutoff region is this random region underneath the curve IB is equal to 0. This is also a proof where when IC is represented in common emitter mode, we see that it comes as alpha I plus ICBO. So basically the collector base minority current. And we get this sort of expression which will result in even when IB is equal to 0, IC approximating being 0.25 milliamperes. And this results in this curve, due to which we get a very distorted cutoff region. Another thing to keep in mind over in this curve is the VCE SAT, or the collector emitter saturation voltage, beyond which the curve is a straight line which is slanted upwards, and before which the curve is exponential in this case. Now, BJT, we have seen the common emitter mode and the common base mode. Common base mode is used as voltage amplifiers, and common emitter mode is used as current amplifiers. There's also a common collector mode which is mainly used as voltage buffers.